Thank you everyone for joining me today. We're going to try and go over some preparative HPLC column issues that people run into and how to select the best way to hit your target compounds as you would hope to. We're going to start first with a little bit of who we are. Teledyne is obviously an instrument manufacturer, but we also do columns for both flash and for preparative HPLC. And we've been around for quite a long time, as you can see, but I'm going to go ahead and skip on to the topics. Right now, here's a little bit of a description of what we consider the differences between flash and prep HPLC. We also have analytical and UHPLC on here as well, but we're going to focus on the top two for today. Typically, flash would be a system that you're running probably 80 to 95% purity, much higher flow rates, and much larger loadings typically. Prep HPLC, we can usually get up to about 150 mils per minute on our system, which is the one you'll see right here right there. So that's our Prep HPLC system that we use, and that's the AccuPrep HP 150. You'll see that a little bit later as well. Next, I'm going to get into the topics for today. I'm going to go a little bit into the normal phase options, when to consider those, reverse phase column options, some of the factors that affect that reverse phase, which would include solubility, pH, also some polarity on your column selection. Column loading is in here, as well as a little bit of special applications using chiral and peptide molecules. And as a teaser, I had put in there that we were going to have some surprise content. Today's surprise content is going to be SFC column options, which there's quite a few, but I'll just give you a few quick points for those as well. Normal phase flash is typically a lower purity, as I had mentioned, and higher loading. Usually it's going to be using a silica column with an organic mobile phase. Reverse phase is going to be typically the opposite of that. We're going to go with more of a non-polar phase, but a polar mobile phase, which would be an aqueous with maybe methanol, acetonitrile, something of that nature. But what do people typically use? What do they have available to them in the lab is what I usually find out. So we'll go considering each of these different column options, and we'll see what might be best for you. So the columns that you can see over here on the right, they're going to be the flash columns, and I'm going to get into them first. Right now, we have a NextGen 300 Plus, which is our typical instrument that we try and use for that type of chromatography, as well as the EasyPrep flash system. Normal phase samples typically have lower resolution on the columns just because of the chemistry of the phase itself. Some of the benefits to it is the fact that people can preload their cartridges with the liquid. They can also do solid loading cartridges, as we have right here on the right-hand side. So you can see that right there. So that's a sample loading cartridge that you can use to put a larger amount of material onto your column. The columns are traditionally silica-based, but we can use C18 and C8 on them as well. Here's a little structure of the silica columns that we offer. There's a diagram over here that you can see, so we can go anywhere from 0.8 grams, 20 milligrams if it's a tight separation, all the way down to 600 grams if it's a very large separation. And you'll see over here that we can get up to almost a liter a minute. That's not the focus of today's talk, so I'm going to now get into the reverse phase and preparative chromatography. That'll be those over here, right here. This is typically what I deal with on a daily basis. So I'm going to go through those columns and their conditions. To do that, again, here's a blown up picture of the prep system that I typically use. We can get up to 150 mils a minute. Our system is optimized for all flows so that we do not lose any material, and we know exactly where our peaks are as it comes through the fraction collector head. Whether we're using ELSD, UV, MS, we can always make sure that our peaks are well aligned. And it also has a very simple touch screen display, so you don't have to worry about an external computer or data delay going back and forth between the computer and the instrument. As you can see here, I put in together at the top, you have the silica column with a little bit of a hydroxyl group sticking off there. And we change and step down as we go down from the amine to the C8 to the C18, we're going to, from a high polarity column to a non-polar column towards the bottom of the C18. Now I'm going to get into some of the factors of solubility, pH, and polarity on your column selection. One of the biggest things that I run into working with customers is that we typically see issues and questions about solubility, what's the best solvents to be using, and what the different factors are that will affect them. Typically, the best condition would be water. Whatever your starting conditions is for reverse series would be basically mostly water with maybe 5 or 10% organic in it. It's great because we get very little effect on the peaks, but the drawback is you have very poor solubility. So people will try to go to the next step and add on more acetonitrile or methanol into their sample, which is good. It helps it solubilize it. But the problem is we also start seeing some distortion of your peaks. DMSO is pretty good because it is extremely soluble. But the downside of it is you can also have a very high solubility for things that you don't want to be soluble. For instance, if you're using palladium catalysts or other type of reaction byproducts that are usually not very soluble in water. So as soon as you take them up in the DMSO and put them onto the system, they have a tendency to crash out, and that's obviously not a good thing. The first set of chromatograms here I will show you has water. Again, as I mentioned before, water is really good at getting a nice peak shape, but the problem is to get the sample into solution, we had to heat it up, and we had some degradation. As you can see, the compound is right there. My suspicion is we actually created a methyl ester from the methanol that we actually had the sample in. We had just a touch of methanol, so we got just enough of a conversion. The methanol is perfectly fine because we didn't have to heat it. The problem is we also don't see too much here. It's a good chromatography and good chromatography there on the DMSO. The drawback is we do have a UV chromophore at 214 to 220 that we can see in the chromatogram, which usually isn't too bad because we can still see the 254. People that use DMF will have both a 214 and a 254 trace for the void, so sometimes that can be a little bit difficult. But as you can see here, we're starting to see a little bit of distortion. The water's still fine, but the methanol is showing distortion on the leading edge. The DMSO, obviously, is still fairly stable. We'll go again, and now we're starting to see a lot of degradation of the peak and resolution from the methanol. DMSO isn't too bad. We have no breakthrough. So as you can see here, there's still no breakthrough on the DMSO. Definitely a breakthrough here on the methanol, but we're still pretty good shape on the water. Now this is where it gets really bad when we go up to a full 2 mil injection. With the methanol, most of our material is actually here in the void. We have very little material back here where it's supposed to be on your regular retention pump. DMSO, we're evenly split, and we've still got some back here, but I would not want to try and chromatograph that. Water, however, is still pretty good shape. The only problem is solubility is still an issue. I'm going to go into a little bit of that later on. If you notice that the compound was actually quite polar, and we were running a very low gradient, very shallow, low gradient, one of the things we can actually look at for polar compounds is actually changing your stationary phase or your mobile phase conditions. So in this case, if you change your mobile phase conditions and go down to maybe a 2% organic, you might be able to get some pretty good chromatography. You might be able to get it to retain and have a little bit more retention on it. The flip side is you also could run into the issue of what we call phase collapse. So your C18 phase can actually collapse on you. So one of the other options is you can, like I said, change your solvents, or you can change your column. So one of the things that we can do with columns is we can put these R groups in here, which are hydrophilic groups, which will allow some of the water to get in there and hydrate the lower portions of the stationary phase, so you don't have as much of a chance of phase collapse. And that will also actually give you generally a couple minute, I'd say maybe a 10% retention shift in your actual chromatography. I would love to have had some of that data for you. Unfortunately, with COVID, I'm having difficulty getting into some of my labs and working with some of my customers to just do random research, and it's pretty much as needed visits. So, but if we decide to do that, we can also go down here and look at a Hillock column. So what that basically is running a silica or a polar type compound, column in a kind of aqueous mode. And it actually is fairly successful in getting the material to maintain on the column. The difficulty is getting a hold of preparative compounds of that nature. So here we have stationary phases, as I mentioned, going down from C18 all the way down to the amino. And the increasing retention based on nonpolar analyte. So if you have a nonpolar analyte, you would want to go more towards a C8 or a C18. If you have a hydrophobic or a polar molecule, maybe we do it on the left-hand side. And you go down, maybe use a phenyl or an amino. So this is a little bit of an explanation of why we have all these different issues with polarity. Is we have protonation and deprotonation going on for acids. So as you can see here, we have two different structures on the salicylic acid that could cause you problems. One is a 2.79, we have pKa. If we take and move it down here on this region, where the pH is quite low, we tend to protonate that hydroxyl group, the acid. If we go very high, we can actually deprotonate both of them. Over on the right-hand side, we have a basic compound, methamphetamine. And as you can see, there's only one phase there because there's only one particular position that we need to worry about, and that is at 10.21. So the pKa of that is something where we would have to go above 10.21 in order to make sure that that compound is in the best way for chromatography, if we're going to run it in basic mode. And these chromatographs obviously are courtesy of Chrome Academy. So what does that mean for you as far as chromatography goes? Well, if you take a look down here, at lower pKa's, it protonates, and we get a chromatography that looks like this. If we are pretty close to the pH and the pKa where they're about the same, you'll get a mixed mode where you'll basically get a broad smeared peak across the chromatogram. If you aren't low enough in your pH, you're going to get the polar compound right here, and it's going to just go straight through the column with the water. It's not going to really retain to the column at all. So now I'm going to get into some column loading and yield and purity requirements, as many of my customers get into. The first thing that you would want to make sure of is that your sample is focusing on the head of the column. And we've actually checked that one off. We can use a larger column diameter. So if we go from a small column up to a larger column, that usually helps us be able to load considerably more than if we were to just say maybe take a longer column. However, one of the ways that we can greatly increase our loading and our efficiency is if we actually use a shallower gradient. So we're going to go into that right now. We have a software feature in our instrument that actually allows us to optimize those gradient profiles. So if we're starting at 10 microliters of an injection, we can actually get a small chromatogram that gives us an idea of what we should actually see or where our best gradient can run. And then we can scale up to 1, 2, or even 5 centimeter columns from that exact same analytical column. However, as you see highlighted here, it must match the stationary phase exactly the same. I've seen people try and run AQ columns with standard columns and get different chromatography. It's going to happen. So we have to match it up, same phase for same phase, same porosity, etc. Let's see. And we can use both purification and analytical on the same run to get exact scale up. The focus gradient generator basically takes a scout method, as we can see right here. So we would choose your column of interest, in this case, the analytical column. We would choose the scout column, And what it'll do is it'll create this very steep gradient that we can actually run our compound on and get a fairly decent chromatogram. Once we get that chromatogram over here, then we click on the button and it says focus. So we basically have the ability to pick on a retention time. Usually I'll try and put it on a peak. In this particular case, we're using just that first of those two peaks. Notice how with that gradient run, we were only about 30 seconds apart. If we go ahead and run that on the shallow gradient, you'll see that we have a very shallow gradient that's only about 10%. And then I can isolate our compound with well over 4 minutes of resolution between the two peaks. What's great about this is it's universal, so we can use any kind of column, silica, C8, C18, or chiral. We can do normal phase or reverse phase, and it's definitely scalable. But as I mentioned before, make sure it's the same stationary phase and same solvent system. So now these are a couple examples of that exact process that I was just mentioning to you. We took a couple of customer samples and we purified them, not knowing exactly what they were. So the customer just handed me this compound and we were able to run it, and in the Scout, it looked like it was a pure compound. I said, well, let's try it again. So we basically did a Scout gradient, and as you can see, it was up to about 80%. This is about where it chose as the optimal point. So we did 5% on each side of that 80. Actually, I think that might have been 10% on each side, so it was probably 70 to 90. But as you can see, we were actually able to purify some material out of that compound and get two separate peaks. Those two peaks were about a 30% impurity on the tail side. And the customer kind of knew that by NMR, but didn't tell us that until after the fact. But this had already passed through their QC and was ready to ship out to a customer prior to us actually taking a look at this. And we were able to save them a couple days and headaches of trying to return the material and reprocess it. We started out with a 1 milligram Scout of the sample, and we were able to actually purify about 30 milligrams of the material per injection. This is on a 3 centimeter column. I think we could have probably loaded a little bit more, but at least we were able to get some purity out of that compound. Whereas before they would have shipped out the same material to the customer thinking it was pure. Another example came from the same customer. They basically gave me a sample that they had difficulty separating on another vendor system. They were able to do about 5 milligrams on a standard run on that instrument. We were able to take that peak, separate it into that, and I'm a perfectionist, so I was kind of disappointed that we were only able to get up to a 20 milligram purification. I was going to try and go up to 25 or 30, but in their view, that was more than well resolved for what they needed. Apparently, they didn't need a whole lot of material, so that was a good thing. Next, I'm going to get into some specific applications, including chiral and peptide molecules. As I mentioned before, normal phase chromatography typically uses silica and a few organics. Reverse phase uses typically C18, maybe sometimes some C8 with water and methanol or acetonitrile. But how many columns and solvents do you use for chiral chromatography? Pretty much you can throw out any number and you're not wrong. You can continue going. With chiral chromatography in the past, I've actually seen people custom design a column that is specifically suited just for their one compound. So you could basically have every compound in your laboratory, have every chiral compound in your library set up to do its own specific column, because that's how specific these columns can be. The nice thing is there's things that we can do to help you with that. This is the chart that comes directly from Chiral Technologies, one of the vendors of chiral columns, probably one of the longer traditioned column manufacturers for chiral chemistries. And in here, you can actually see that you're supposed to go through certain types of alkane and alcohol mixtures. get a particular resolution factor, K primes, and then you either increase or decrease based on where that is. And that could be a vicious, endless cycle if you choose to go that route. I, however, have come across an ability to do something with one of our customers where we just basically ran a column that they had in the lab. We ran a scout on it, and we ran the gradient profile, similar to what I mentioned to you earlier with the focused gradient. And as you can see, we got a separation. So we had a partial separation, so we went back and had the software tell us what optimal percentage we should actually be looking at in this case. And we were able to actually isolate this chromatogram from that previously run chromatogram, where we have about 3 minutes between the two peaks. With that, we were able to develop a 20x folding scale-up factor over here, and we still had some resolution that we could have probably even gone a little bit more. Another thing we've done in the past is peptide applications. We're getting more and more into this this year, as I've only been with Shimano I came from Shimano about a year ago to Teledyne ISCO. And since then, we've been trying to break into new markets and work into different applications. And this is actually one of them. So one of the things that a colleague of mine had done is actually, this is an application note that you can find on our website. But it was basically an ACE inhibitor peptide. And it was a very high molecular weight material. But the blue trace that you can see right here on the chromatogram was actually using our mass spec. So we could actually define the different compounds and different specific molecules of this peptide. It was on a 2 centimeter by 15 centimeter C18. It's a fairly shallow gradient. What we could have also done is we could have also gone to a C8 column, and that's some of the work that I want to start doing in the future, is doing some of these C8 to C18 comparisons, and maybe some other phases, like a phenyl or some other stuff. But anyhow, this worked out fairly well and was able to save the customer a great amount of time and cost in trying to purify and obtain material for the process. The next thing I'm going to get into is what we have to do in many circumstances with peptide and chiral is load very large amounts of material. Usually an injection from a manual loop or an auto sampler is difficult if you have to do maybe 50 mils, 100 mils, or even up to a liter of material. So how do you do that? We can use a loading pump on our systems and actually load large amounts of material. The problem with loading large amounts of material is the chromatograms I showed you earlier, where if your compound has some methanol in it or some other solvents in it, you can potentially get breakthrough and bleeding through your system. So what we would typically try to do is find a way to try and adhere the compound to the head of the column. That was our first thing that I mentioned to you earlier in that one slide, where we want to make sure that the compound focuses. So in this case, what we tried to do is I set up an injection for a protein customer or a peptide customer of ours. The first compound, we had 2 different components. As you can see, it's fairly good resolution. I mean, I would go ahead and run with this. It's not too bad. But the problem is, if we try and load up that same amount of material by having a large injection, we go from a resolution that's decent to something that there is no way that you can get that to be pure. We can get the back peak to be a little bit pure, but your first component is never going to be pure. What we did is we basically pumped on a sample with a dilution of methanol water. It should be 50-50 there. But, so we basically took a 10 mil injection and loaded it with a auto sampler. Actually, I think this might have even been a manual injection as well. But basically, we put 10 mils of that same material onto the column, and that's what we were able to obtain. I chose to do something different, and I loaded with a loading pump for about 2 minutes. I diluted the material down, and I had the system running at, I think, about 5 to 10% of the starting condition. So we were at about 5% organic. So we were running that at the exact same time that we were pumping with our loading pump. So we had a total of a constant 20 mils going into the column, 10 mils of each. And once we finally got the entire material loaded on, as you can see, we had a drastically improved resolution between those two peaks, and we can load, I'd say, at least 4 or 5 times more by doing this dilution method as opposed to just doing a straight 1 mil injection onto the column. So now for our surprise content. We're just starting to look into the possibilities of seeing an SFC system in our future. So we're starting to do some work with SFC columns and with some of the customers that we have out there that are actually doing some SFC. And so the next couple slides will actually go into that. One of the people that I've worked with in the past prior to coming to Teledyne was Matt Prispisol from ES Industries. And with his blessing, I've taken a couple of his slides that I've used in the past. The compounds that he's running are all analogs off of a caffeine, which is fairly polar compound. So we have caffeine, theophylline, theobromine, and paroxetine. We basically he took those 4 compounds and ran them in different conditions on in one of his SFCs. These are the columns that he used to evaluate the system. We have the green step basic, and ethylpyridine, and the green step silica. Now the difficulty with SFC is with reverse phase, typically you're using 1 column. You're typically using a C18, maybe you get into a C8. With normal phase, you have a silica column, maybe like an alumina column or something like that, but it's not too bad. A couple choices and you can get a pretty good resolution on most compounds. The problem with SFC is there's so many different options for columns based on the chemistries that you're dealing with that you almost need to be able to have a multi-system scouting ability. So we would basically do different solvents, different columns, and see what we can come up with. But as you can see here, these are the basic 8 columns here, but this is only the bulk of the columns. There are also others out there that are very special columns as well. We're going to try and work with ES to help provide us with some of those oddity columns as well if we need to in the future. So getting to the chromatograms, the 3 different injections, as you can see, these are all at 400 bar for the back pressure regulator. So we have 400 bar across all of them. They're all using the same 10% methanol as an additive. If you look at the silica column over here, you basically get 3 distinct peaks where 1 and 2, the caffeine and theophylline, are pretty much co-eluting. We can come over here and we get a little bit more resolution when we get over here to the pyridine column, but still not well enough resolved to do any type of separation. Now if we come over here to the basic, we can actually get a very strong resolution amongst all those columns. If you were to notice the actual structures on all those compounds, I'll go back to them, there's a lot of nitrogens in those individual compounds. So it will basically make sense that we want to look at a basic column. Fortunately, with the methanol in there, we actually are creating an acidic environment, just slightly acidic, so that we don't need to put in acid modifiers like you would normally on, say, reverse phase chromatography. Now, this is another slide for SFC. It's actually a little bit more interesting because what we're looking at here is a 400 bar versus 100 bar. So instead of just having to worry about solvents and columns, now we actually have to throw in the added unknown of what your pressures are. Usually it's not significant of a difference when you change your pressures, but in this particular case, you can see that we came way in on our retention. Resolution is probably, our alphas or K primes for each of those compounds are probably fairly similar. But if we're going to stack injections, they're much sharper We can probably load as much, but we have a much shorter retention time, so we can actually stack on injection after injection and have a much higher throughput of material. So that's the benefit of having the shorter run times. Next, I'm going to get into some chiral compounds that I ran myself prior to coming to Teledyne. And this is basically a plethora of columns from Chiral Technologies. As I mentioned, I showed you the slides earlier. What I want to show most importantly is the fact that we can do different things with different modifiers. So each one of these individual columns can perform differently in SFC. The IA, AY, and OZ, as you'll notice, are highlighted. And we'll show you why in a second. But this is using methanol as a modifier for Omeprazole. I'm sure somehow, I guess, I cut off the compound name on the actual picture, but you can see it at the top. So we have an IA, AY, and OZ, and all of them look fairly similar when you're running methanol. But I would say that for throughput and consistency's sake, the IA and the AY would probably be very similar columns, would be good columns to use, and would actually provide the best cycle times for doing preparative. However, you could use OZ. ID is way, way too long. Now, what happens if we choose to say ethanol, which is another modifier they use in SFC? We do not have enough resolution here. These peaks collapsed on each other, so that wouldn't be good enough. The A and Y actually went further apart. So two different columns, changing just the mobile phase, completely went the opposite directions. So there's no specific silver bullet, if you will, for SFC. It's basically a trial and error with modification of modifiers, phases, and pressures. If you'll notice the OZ over here, the other one that I had highlighted, it's actually pretty much the same between both chromatograms. So we're coming close to the end of our time. So in conclusion, I'm going to say preparative chromatography and scale-up can be complicated and time-consuming, but with practice you can get there, but you don't have to. Don't forget, you're never alone. We're always here to help you succeed. So with that, I'm going to turn it back over to Sharon, and we're going to open it up for your questions. Some of them now, or if you have hopefully sent some in ahead of time, that would be great as well. Thank you, Sharon. Thanks for inviting me over.
And thank you, Todd. We will open it up for questions. Please enter your questions through Q&A, and Todd will provide answers.
I do want to also mention, I forgot on these slides, the SFC portion. Acetonitrile was also another modifier I've chosen in the past and ran with those, but it didn't show any results that were beneficial or any better than what we were able to get with methanol or ethanol, so I just left them out. And I also want to apologize because it looks like with the lag and timing of Zoom, my pointer that was magnifying things was glitching on me, so I apologize for that as well. So any questions? If not, I can get into some from what we had earlier today. Don't see anything in my Q&A section area. So one of the questions that I had from earlier, showing the slide demonstrating flash and prep chromatography. I'm not sure if I actually understand which slide you're talking about. Let me see if I can bring it up. So I gotta share this. I'm gonna try and see if I can look for it. So what I'm doing is I'm scrolling through the slides in a separate window, so I can share that specific window. I don't see any slides where I have flash and prep side by side. The very first one? Okay, let me share that screen up. So what I have here in the background, this slide right here. Let's see. Because I don't see too many chromatograms. I think this is what you're talking about. Okay, perfect. Yeah, there you go. By the way, if you see some slides in here or information you need, we will be providing a link to a YouTube video of this session as well. So you can always go back and freeze time and go into the individual areas of the talk and actually stop and hold if you want to take some information down, whether it be part numbers or data or even screenshot some of the chromatograms. So there you go. Any other questions before I get into some of the other ones? I'm going to stop sharing my screen. Sharon, do you want to go ahead and take back over for the main screen?
Sure.
And in the meantime, I'll go over some of the questions that we had posed to us this morning. One of the better questions actually that I didn't get into is, with the PDA technology that is used in the HP 150, is it enough to consider the purity of the purified samples? And the answer is, I typically do. I would say that if I'm running purity like that, I can get a ballpark of whether or not it's pure or not, just based on seeing the different UV spectrum across the peak. I've done it before in the past with just even a dual UV detector, where I just basically take the two different wavelengths and compare them to one another. But if you do have to have absolute purity, or at least a mass check, we would suggest either using ELSD for the mass amount or a mass spec to actually get the purity identification of a compound based on its actual mass. And as far as another question was whether or not we can have something to run at 100 mils a minute and possibly use up to 10 liters, is there an efficient space for that amount of mobile phase? What I suggested is we would use either carboys or glass, kind of like glass vessels, 10-liter vessels. And then our sample inlet lines actually have a pressure line that goes into them that can actually gauge the level of the solvent. So we don't have to worry about running out. So if it notices that the large Nalpac or steel can that you're using for solvents is running low, it'll let you know, and it'll basically just pause the system and ask you to go ahead and replace the solvent or continue. So we can actually take care of large volume solvents and not running out. And that's pretty much it. Are there any other questions? And the answer to these is